Hello and welcome back to Educator.com and welcome back to Biochemistry. So today we're going to start talking about acids and bases. This is going to be a reasonably quick review because again we just want to get our feet wet, get used to some concepts from general chemistry before we actually dive into the biochemistry proper. So acids and bases. Acid-base chemistry is profoundly important. We're going to be going through most of the stuff that you've seen. We're going to be talking about pH. We're going to be talking about how acids and bases behave. What I'd like you to take away from the notion of acid-base chemistry is how acids and bases actually behave, and the idea that the only thing that moves in an acid-base reaction is the proton, is that hydrogen ion. If you can concentrate just on that aspect, you can use what you know about your intuition that you've gained from general chemistry and from organic chemistry to actually understand a huge amount of biochemistry. Don't get lost in the details here. I mean, yes, the details are important, but what's important is understanding that it's only a proton that's moving. That's it. That's the only thing that's going on here. That's the important part to take away from this. Okay, let's go ahead and start our review. Let's go ahead and begin with water. So, let's begin with H2O. Okay, so H2O, water in solution, actually dissociates a little bit. It releases a free hydrogen ion and it releases a free hydroxide ion. So we write that this way as H plus OH minus. Now, you remember from general chemistry that now we want to be able to have some sort of a numerical measure of the extent to which something dissociates. In other words, how much H plus, how much OH minus is floating around in water. Well, you remember there's something called the equilibrium constant. You have some reaction. What you do is you take the concentration of the products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients. Now let me go ahead and put some state symbols here. This is AQ and this is AQ. And you remember, of course, when we have liquids or solids, they actually don't show up in the equilibrium expression. So in this case, our KEQ is going to equal the concentration of H plus times the concentration of OH minus. But again, this is liquid, so it doesn't show up in the denominator, so that's all. Now we call this, because it's for water, we give it a special symbol, Kw. We've measured this, and it's actually equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius. So at 25 degrees Celsius, this ion product constant, this dissociation constant for water, happens to be 1.0 times 10 to the negative 14. That's a very small number. What that's telling you is that most of it stays as water, but a little bit of it, very little, dissociates into that. Okay, that's it. So this is a very important relation. Now, in any and every aqueous solution, the hydrogen ion concentration times the hydroxide ion concentration has to equal 1.0 times 10 to the negative 14. In other words, if the hydrogen ion concentration rises for some odd reason, the hydroxide ion concentration drops because their product has to equal a constant. That's what this whole idea is. A constant is something that doesn't change. The particular values of the individual species involved in the constant, they might change, but their product doesn't change. So if one goes up, the other has to go down. Okay. Now let's introduce something called the p-scale. You already know this, but we will mention it anyway. So we talk about pH, and that's equal to negative log of the hydrogen ion concentration. pH was used, again, hydrogen ion concentrations are generally very small, things like 2.6 times 10 to the negative 3, very tiny numbers. So instead of dealing with those numbers, they developed this idea of a p-scale because they wanted to deal with numbers that are just more natural, like 6.2, 10.6, things like that. It doesn't really matter. I personally prefer to deal with concentrations directly as opposed to taking the negative logarithm of them and using the p-scale. But in biochemistry, they tend to use the p-scale almost exclusively. So that's all it is. It's just the negative log of whatever concentration. We also speak of a POH. That's the negative log of the hydroxide ion concentration. You can also talk about, let's say, PCl. That's equal to the negative log of the chloride concentration. It could be P anything, so P scale. But most of the time, we talk about pH. We pick one thing to discuss as our standard in a particular aqueous solution. We've chosen the hydrogen ion concentration as the standard against which other things are measured. Okay, so let's see. So if the hydrogen ion concentration times the hydroxide ion concentration in any aqueous solution is equal to 1.0 times 10 to the negative 14. Well, in terms of pH, if I take the negative log of both of these, I get the following. I get the fact that the pH plus the POH of an aqueous solution is equal to 14. They're the same thing. One deals with concentrations directly, the other deals with a different representation of concentration. That's all. Okay, so a pH of, well, actually I'll introduce that in just a second. Okay, so let's see what we have here. So let's do an example just real quickly. Okay, the pH of a glycine solution. Glycine is an amino acid, and we'll get to that in just a couple of lessons when we start to discuss proteins, is measured to be 5.4. Okay. The question for us is, what is the hydroxide ion concentration? What is the hydroxide ion concentration in the solution? Okay. Well, nice and easy. We just use this right here. That's our basic relation. So, okay, the pH. So if the pH of our solution is equal to 5.4, well, that implies that 5.4 equals negative log of the hydrogen ion concentration. That's the definition, right? So let's go ahead and take the antilog, okay, raise it to the power. That means the hydrogen ion concentration is equal to 10 to the negative 5.4, right? Move the negative sign over, antilog, just take 10 to that particular power. And when we do that, we get 3.98 times 10 to the negative 6 molarity. So the concentration of hydrogen ion in this particular glycine solution is 3.98 times 10 to the negative 6 moles per liter. Okay, well, we know that the hydrogen ion concentration times the hydroxide ion concentration is equal to 10 to the negative 14, right? 1.0 times 10 to the negative 14. Therefore, the hydroxide ion concentration equals 10 to the negative 14 divided by the hydrogen ion concentration, which is 3.98 times 10 to the negative 6. And when we do this calculation, we get, what do we get? 2.51 times 10 to the negative 9 molarity. That's it. Nice and simple. Basic relation. Hydrogen ion concentration times the hydroxide ion concentration at 25 degrees Celsius is 10 to the negative 14. If I have one, I have the other. If I wanted to go to pH, if I wanted to, let's say, do the POH, what I would get is the following. POH, I would just take the negative log of this hydroxide ion concentration, and I get 8.6. Nice, straightforward, nothing strange going on here.